Inside the skin of an F-35, the aircraft functions as a data processing hub, managing a vast network of internal sensors that drive modern battlefield awareness. To understand why this hardware exists, we have to look back at the mandate that forced its creation. In the 1990s, the Pentagon launched the Joint Strike Fighter program. The military operated a massive fleet of specialized aircraft, and the objective was to consolidate those distinct roles into a single universal airframe. The first requirement was to replace the Air Force's dogfighters, like the F-16 Fighting Falcon. The new jet needed to match that aircraft's supersonic profile and agility. Simultaneously, the design had to replace the A-10 Thunderbolt II, requiring the armor and internal volume necessary to support ground troops with heavy payloads. The final requirement came from the Marine Corps. The new aircraft needed the same vertical takeoff and landing capabilities as the AV-8B Harrier, allowing it to operate from small ships and austere bases. Forcing supersonic airframe geometry to resolve the conflicting physics of heavy ground attack and vertical hovering created an intense structural paradox. This mandate required engineers to reconcile aerodynamic needs that were previously considered physically incompatible. The aircraft's exterior geometry is designed to manage radar energy. The continuous curvature of the fuselage and the specialized application of radar-absorbent material work together to trap or deflect incoming signals. Stealth requires a sacrifice in how the jet carries its weight. External missiles create a significant radar return, so to remain undetected, the F-35 stores its primary weapons entirely within internal bays. Beneath the radar-absorbent skin, the jet relies on sensor fusion. This software architecture takes raw data from the radar, electronic warfare sensors, and cameras, compiling it into a single, cohesive view of the battle space. A critical part of this network is the distributed aperture system. 6 infrared cameras are flush-mounted. They provide a constant 360-degree thermal view of the surrounding environment. That thermal data is projected directly onto the visor of the Gen 3 helmet-mounted display system. By tracking the pilot's head movements, the system allows them to see through the cockpit structure and look directly at targets on the ground below. This visibility allows the F-35 to locate targets and process data across multiple spectrums, giving the pilot the ability to engage before the aircraft is even detected. Eventually, the goal of a single universal jet diverged into 3 distinct variants. While they share a similar silhouette, they are built with different skeletons, sharing only about 20% of their physical components. The F-35A is the conventional variant for the Air Force. It is the lightest and most agile of the 3, equipped with an internal 25mm cannon and a structure rated to withstand 9 Gs of stress. The F-35B is built for vertical flight. A drive shaft engages a lift fan behind the pilot, while the main engine nozzle swivels 90 degrees downward to provide the thrust to hover. The Navy's F-35C is built with reinforced titanium bulkheads to survive the shock of catapult launches. Its significantly larger wing area provides the lift needed for low speeds required during carrier landings. Accommodating these environments required extreme weight reduction and new developments in material science to ensure the airframe could survive wildly different mission profiles. Powering the entire fleet is the Pratt & Whitney F-135. However, as the aircraft receives new Block 4 software and sensor upgrades, the electrical and cooling demands are reaching the engine's original thermal limits. Current engine cooling capacity falls short of rising Block 4 demands. A new adaptive cycle engine was explored, but massive costs threatened aircraft production. Instead, the military chose the cost-efficient engine core upgrade, retrofitting all 3 variants with improved performance. This decision reflects the reality of modern defense programs, where managing the physics of flight is often a negotiation between thermodynamics and the federal budget. The F-35 program has faced 2 decades of intense scrutiny, driven by high production costs and schedule delays that have redefined the scope of military acquisition. The aircraft's primary role in combat is to serve as a networked coordinator. Its sensors collect data and feed precise targeting information to older aircraft and naval destroyers that lack these advanced systems. By acting as a force multiplier, the jet increases the combat effectiveness of every other asset in the fleet, allowing the entire force to operate with greater situational awareness. Beyond the engineering schematic, the F-35 Lightning II functions as a primary sensor node for active combat operations. The F-35 Lightning II ultimately realized the 1990s mandate for a multi-role platform, integrating 3 distinct missions into a single, networked system that continues to define the requirements of modern aviation.